Today's class, we are going to solve an ordinary differential equation by using method of variation of parameters. So it is like usual. We already saw that solving our ordinary differential equation has two parts. That is, it has the complementary function and the particular integral. Here again, for solving the ordinary differential by using method of variation of parameters also, you have a complementary function and a particular integral. The complementary function here would be same as the normal way of solving it. That is, we'll be having three cases. Case 1 where you're having a real root and it should be different. When you're finding if the roots are real and they are different means you have case 1. The second case is it's real and they are same roots, you have case 2. And the third case is when you have imaginary roots, your solution for your complementary function, you have three cases. So the same thing you'll be using it for the method of variation of parameters. The complementary function doesn't change. But here, the way of finding a particular integral will change. So before seeing how the particular integral will change, first, where do you use this method of variation of parameters? So this method of variation of parameters, it can be used only for the ordinary differential equation of order 2. The highest order should be 2. That is, equation of the form y double dash plus py dash plus qy is equal to x. So if your given equation is of this form, it should be a second order differential equation. Only in this case you can apply your method of variation of parameter. Okay, so here you're having your right hand side to be capital X. This X is nothing but a function of X. It can be any function of X. Here, while doing your normal ordinary differential equation, you had restriction. It should be an exponential term, sine term, or a cos term, or it should be a algebraic term. But here in this case, when you are considering for an ordinary differential equation, your right hand side can be any variable of x or any function of x, but you can use this method of variation of parameters for all the problem. Here you have some restriction. Okay, so now method of variation of parameter. So if your equation is of order 2 only, this method can be applied. Here you are given p, q and x. All these are some functions of x. Okay, so as usual, your complementary function, finding the solution of a for an ordinary differential equation, your solution has complementary function and particular integral. So here your complementary function, again it is divided into three cases. When the roots are real and distinct, this is how. That is a e m1x plus b e m2x. So this is your complementary function. Second one, when the roots are real and same, we'll be having ax plus b into e power x mx as your complementary function. Likewise, when you have a pair of imaginary roots, this is how you write your complementary function. Okay. So here in your method of variation of parameters, you write your particular integral. Previously, you had three cases, right? For an exponential term, you will write a different particular integral. That is, you substitute d is equal to a here. For a particular integral sin ax or cos ax, you substitute d squared is equal to minus of a square. And for exponential, you will use your binomial expansion. But here, for a particular integral, whatever be your right hand side, you will be using this standard formula to find your particular integral. So here you can see that you have terms y1, y2, x, w, all these terms you are having. Okay, so y1 and y2 are the solutions. They are the solutions of the given equation. Okay, so what is the solution of this equation is you're writing the complementary function, right? That complementary function is the solution. Since it is of order 2, you'll be having only two constants. Okay, so when you're writing the complementary function, since the order of the equation is 2, you'll be having only two constants. So whatever comes with the constants is called as your solution. So if I'm taking case 1, you can see that e m power em1x. em1x is coming along with my a. Okay, so y1 is nothing but em1x. Likewise, along with my p, I have em2x. So y2 is nothing but em2x. Okay, this is for case 1. For case 2, I'm having ax plus b equal to e power mx. Okay, so when I multiply this inside, it will be ax e power mx plus b into e power mx. So for case 2, my y1 will be x e power mx plus, sorry, this is y1 and y2 is e mx. Okay, so this is how my y1 and y2 will be if it is case 2. For case 3, you can see that it will be a, if I multiply this e power alpha x, it will be a cos beta x e power alpha x plus b sin bx beta x into e power alpha x. So my y1 here will be cos beta x e power alpha x and y2 will be sin beta x into e power alpha x. Okay, so this is the outline. This is how my y1 and y2 will be. Whatever you have along the constant in your complementary function is your solutions, that is your y1 and y2. Okay, so now you know this is your equation to find your particular integral. So in this equation, your y1 and y2 are nothing but they are just the solution. That is, in your complementary function, whatever comes along with your constants a and b, that is your y1 and y2. This capital X here is nothing but in your equation. You have seen I have a general equation. This is my general equation, right? The right hand side of the given equation is my capital X. Okay. Now I have another term W. So what this W is, it is called as the Wronskian. It is named as Wronskian and it is denoted by capital W. So W is nothing but the determinant of y1, y2, and here it is the first derivative of y1 and the first derivative of y2. When you find the determinant value, this is called as w. Okay, so when you put inside the formula and you solve the formula, whatever answer you get is the solution of the given ordinary differential equation. So in today's class, we are just going to solve one problem. So this problem will make you clear about the concept. Okay, so the first problem is solve d square y by dx square plus 4y is equal to tan 2x. Okay, so here as we know that we denote d by dx as capital D. So this you will write it as dy plus 4, sorry, d squared y plus 4y is equal to tan 2x. So here both the terms are having y as common. So d square plus 4 into y is equal to tan 2x. So this is the symbolic form of the equation. Now I'm going to write the auxiliary equation. The auxiliary equation I have to write in terms of m. So m square plus 4 is equal to 0 or m square is equal to minus 4. From this m, when I'm taking the square root of minus, it will be I. So it is plus or minus, square root of minus is I, square root of 4 is 2. Okay, so it is like 0 plus or minus 2i. So in writing the complementary function, this is of case 3. So your complementary function, you will write it as e power alpha x. This I'll just write the general form first. It is e power alpha x, a cos beta x plus b sine beta x. Because you're having imaginary root, you go for case 3. This is your alpha and this is your beta. Okay, so now in the place of alpha, it is e power 0x, a cos. In the place of beta, you're having 2x plus b sine 2x. Okay, anything to the power 0 is 1. So this term will become 1. So it is a cos 2x plus b sine 2x. Okay, so now we found what is the complementary function. This is your complementary function. Now we have to know what is our y1, y2, capital X, and what is w. So y1, as I told you, here my constants are a and b. So whatever comes along with my constant a is called as my y1. So it is cos 2x. Constant b, I have sin 2x. So that is my y2. My right hand side is capital X. So this is my given equation. It is right hand side of the given equation is tan 2x. Okay, it is tan 2x. Now I'm going to find what the Wronskian of this is. So it is y1, y2. This is y1 dash, y2 dash. Okay. So for I know what is y1 and y2. For solving this, I need what is y1 dash and y2 dash. So y1 dash is nothing but the differentiation of cos. Differentiation of cos is nothing but it is minus sign. So it is minus sin 2x. The differentiation of 2x is 2. So it is 2 into sin 2x. Likewise, when I differentiate my sin 2x, differentiation of sin is cos 2x. Again, differentiation of 2x is 2. Okay, so now I have all the values. Now I'm going to find what my w is. So it is cos 2x sin 2x. Here it will be 2 sin 2x and 2 cos 2x. Okay, now if I cross multiply, it will be 2 cos square 2x minus of minus 2 sin square 2x. Okay, so it is 2 cos square 2x minus and minus will become plus 2 sin square 2x. And both the terms are having 2 as common, so 2 is taken outside. So it is cos square 2x plus sin square 2x. I know that cos square plus sin squared is 1. So it is 2 into 1. So this is 2. Okay, so now I have all the values. I have to write what the particular integral is. So I'm just writing the formula. Particular integral is nothing but minus y1 integral over, sorry, integral y to x w into dx plus y2 integral y1x w into dx. Okay, so now I'm going to substitute all the values here. So my y1 value is nothing but minus cos 2x, y2 value is sin 2x into capital X. I'm having right into capital X is the right hand side, which is tan 2x divided by the Wronskian value. We found it to be 2 into dx plus y2 is nothing but sin 2x integral cos 2x tan 2x by 2 into dx. Okay, so now what I do is I know tan theta is equal to sin theta by cos theta. Okay, so tan 2x I can write it as sin 2x by cos 2x. So this is minus cos 2x. This 2 I'm taking outside. Okay, so it is integral sin 2x into, instead of tan 2x I'm writing it as sin 2x divided by cos 2x dx. Likewise, in the second integral also I'm writing the same thing. Taking 2 outside, cos 2x I'm writing as it is. Instead of tan 2x I'm writing it as sin 2x divided by cos 2x into dx. Okay, so here again what I do is sin 2x into sin 2x is sin square 2x divided by cos 2x dx plus sin 2x divided by 2. Here cos and cos will get cancelled. It is sin 2x dx. Okay, so now I know that sin square theta plus cos square theta is equal to 1. Or I can write sine square theta as only keeping sine square to one side, bringing the cos square to the other side. So it is 1 minus cos square theta. Okay, so here I'm having sine square 2x. So I'm going to substitute it as 1 minus cos square 2x. So minus cos 2x I'm writing as it is. Instead of sine squared x, I'm using this formula. So it is 1 minus cos square 2x divided by cos 2x dx plus sine 2x by 2. Integral of sine is, I'm integrating this. So it is minus cos 2x divided by 2. Okay. So now it is minus cos 2x by 2. I'm just splitting the denominators. So it is 1 divided by cos 2x minus cos square 2x divided by cos 2x into dx plus, okay. So minus into plus will be minus sine 2x cos 2x divided by 4. I've just multiplied this inside. So it is plus into minus is minus sine 2x into cos 2x divided by 4. Okay. So it is equal to minus cos 2x by 2. 1 by cos 2x is nothing but it is secant 2x. So one of the cos 2x and one of the cos 2x will get cancelled. So it is minus cos 2x dx minus sine 2x cos 2x by 4. Okay. So it is minus cos 2x by 2. Integral of secant 2x is integral of secant x is log of secant x plus tan x. This is a formula. So here integral of secant 2x is nothing but log of secant 2x plus tan 2x. So this is the integration of secant x. But here we have 2x, so we have to differentiate it and write it as the denominator. So it is 1 by 2 into log of secant 2x plus tan 2x. And here for the integration of the second term, integration of cos 2x is sine 2x divided by 2. Whole thing. So this is for common for this cos 2x by 2 minus sine 2x cos 2x by 4. Okay, now I'm multiplying this cos 2x by 2 inside. So it is 1 by 4 into log of minus 1 by 4 and I have minus log of secant 2x plus tan 2x into cos 2x, and here it is minus and minus will become plus cos 2x sin 2x divided by 2 into 2 is 4, and here I will be having minus sin 2x cos 2x by 4. Okay, so these two things will get cancelled because it's the same term. So my complementary function, sorry, my particular integral is equal to minus 1 by 4 into log of secant 2x plus tan 2x into cos 2x. Okay, so now I'm going to write the complete solution. Complete solution is nothing but complementary function plus particular integral. So my complementary function for this problem was a cos 2x plus b sin 2x. This is the complementary function, plus particular integral is minus 1 by 4 log of secant 2x plus tan 2x into cos 2x. Okay, so this is your complete solution. So this completes the problem. Thank you.